It's not a black hole. It's not an asteroid. It's not a nearby supernova. It is the star you see every single morning, the sun. And scientists now say, our sun may be capable of something once thought impossible, a superflare. No guessing, just the facts. And the incredible part is, this isn't based on science fiction. It's based on real observations of stars, almost identical to our own. If the evidence is correct, the biggest solar storms in recorded history may represent only a tiny fraction of what the sun is capable of producing. No guessing, just the facts. In 1859, telegraph stations caught fire. Operators received electric shocks. Auroras appeared over Cuba and Hawaii. The event became known as the Carrington event. For more than a century, scientists believed that represented the upper limit of our sun's power. But new observations are challenging that assumption. Astronomers studying thousands of sun-like stars have found something unexpected. Some of them produce eruptions hundreds of times more energetic than anything humanity has ever witnessed from our own star. They're called superflares. The question is no longer whether superflares exist. The question is whether our sun can produce one. And if it can, what would happen to a civilization built on satellites, power grids, GPS, and the internet? No guessing, just the facts. The day scientists changed their minds. For decades, solar physicists believed the sun had limits. Large solar flares happened regularly. Powerful coronal mass ejections occasionally erupted. But a true superflare? That seemed impossible. Then space telescopes began watching other stars. In 2009, NASA launched the Kepler Space Telescope. Its mission was simple: search for planets by measuring tiny changes in a star's brightness. But while Kepler searched for planets, it accidentally collected one of the largest databases of stellar activity ever assembled. More than 150,000 stars. Observed continuously, day after day, year after year. Hidden inside those observations was something nobody expected: perfectly ordinary stars. Stars almost identical to our own sun, suddenly becoming hundreds of times brighter, not because planets passed in front of them, not because they exploded, because they released enormous bursts of magnetic energy, superflares. Some released 10 times more energy than the Carrington event. Others released 100 times more. A few were even larger. At first, astronomers were skeptical. Maybe these stars weren't really sun-like. Maybe they rotated much faster. Maybe they were much younger. Maybe they had unseen companion stars affecting the measurements. Those explanations seemed reasonable, until researchers kept looking. Over the next decade, more observations arrived. The European Space Agency added new measurements. Ground-based observatories confirmed the stars existed exactly where expected. Then came one of the most detailed analyses yet. A 2024 study published in Nature examined how often sun-like stars produce superflares. The researchers compared stellar magnetic behavior with everything known about the sun. Their conclusion surprised many experts. A star almost identical to our own may be capable of producing a superflare. Not every year, not every decade, but perhaps once every century, or over longer timescales depending on stellar conditions. Scientists continue to debate the exact frequency, and there is still uncertainty about whether the modern sun can generate the largest observed superflares. But the possibility can no longer be dismissed outright. No guessing, just the facts. The sun is entering its most active years. Here's what makes this discussion more than a historical curiosity. The sun is not constant. It follows a natural magnetic rhythm, known as the 11-year solar cycle. During solar minimum, the sun appears relatively calm. Few sunspots, fewer flares, fewer coronal mass ejections. Then the cycle slowly builds. Magnetic fields become tangled. Sunspots multiply. Solar eruptions become more common. Eventually, the sun reaches what scientists call solar maximum. This is the period when the sun is at its most active. NASA and NOAA have been monitoring this cycle continuously using satellites, solar observatories, and ground-based telescopes. The current cycle, Solar Cycle 25, has surprised many researchers. Early forecasts suggested it would be relatively weak. Instead, activity has climbed faster than expected. Large sunspot groups have repeatedly appeared across the solar surface. Several have been visible to the naked eye with proper solar filters. Powerful X-class flares have erupted. Multiple coronal mass ejections have raced into space. Some have reached Earth. In May 2024, one of the strongest geomagnetic storms in more than 20 years struck our planet. Auroras spread across Europe, across North America, across parts of Asia. Even regions that rarely see northern lights suddenly watched the sky glow with shades of red, green, and purple. For millions of people, it was beautiful. For scientists, it was a valuable reminder. The sun remains capable of producing major space weather events. Fortunately, that storm was nowhere near the energy required to qualify as a superflare. Power systems experienced limited disruptions. Some satellite operators adjusted spacecraft positions. High-frequency radio communications were briefly affected, but modern forecasting helped reduce many of the risks. This is one of the biggest differences between today and 1859. We don't simply wait for solar storms anymore. We watch the sun every minute of every day. NASA's Solar Dynamics Observatory continuously images the solar surface. The ESA and NASA Solar Orbiter studies the sun from unique angles. The SOHO spacecraft, operating since 1995, continues monitoring coronal activity. NOAA's Space Weather Prediction Center analyzes incoming data around the clock. Together, these missions provide something humanity has never had before. Warning. Not perfect warning, but enough time to prepare for many solar storms before they reach Earth. The challenge is that magnetic activity remains one of the most difficult problems in solar physics. Scientists can often identify active regions. They can estimate probabilities, but predicting the exact moment a major flare will occur remains extremely difficult. It's similar to forecasting earthquakes. Researchers understand the conditions that make them possible. Predicting the exact timing is another challenge entirely. That uncertainty becomes even greater when discussing superflares. No one has ever observed one occurring on our sun. No guessing, just the facts. Could we actually see one coming? Imagine waking tomorrow morning. The sun looks completely normal. From Earth, nothing seems unusual. Yet 150 million kilometers away, magnetic energy has been building for weeks. Invisible, silent, waiting. The first indication would likely come from spacecraft watching the sun continuously. Satellites such as NASA's Solar Dynamics Observatory detect changes in ultraviolet light that human eyes can never see. Within seconds, instruments would record an intense flash. X-rays would surge across the solar system at the speed of light. 8 minutes later, those X-rays would reach Earth. Radio operators could experience immediate disruptions. High-frequency communications might suddenly fade. Aircraft flying polar routes could lose reliable radio contact. Navigation systems could begin experiencing interference. Then scientists would wait for the next stage. If the flare launched a coronal mass ejection toward Earth, the cloud of charged plasma would travel much more slowly. Depending on its speed, it might arrive in roughly 1 to 3 days. That delay is critically important. It gives governments, satellite operators, and power companies precious time to prepare. Electrical utilities can temporarily reduce stress on transformers. Satellite controllers can place spacecraft into safer operating modes. Astronauts aboard the International Space Station can move into better shielded areas if radiation levels rise. Airlines can reroute flights away from the poles. These protective measures are already part of modern space weather planning. They are designed for severe solar storms, similar to those that have happened before. A genuine superflare, however, raises a different question. Would today's preparations be enough? Scientists don't yet know, because humanity has never had to test them against an event of that scale. Computer simulations suggest that extremely powerful geomagnetic storms could induce large electrical currents in long transmission lines. Those currents could overheat transformers. Some satellites could experience radiation damage. Navigation accuracy might decline. Communication systems could become unreliable for a period of time. Exactly how severe those effects would be depends on many factors. The strength of the eruption, its magnetic orientation, its speed, Earth's own magnetic field, and whether the plasma cloud is aimed directly at our planet or misses us almost entirely. Space weather is not simply about how powerful the sun becomes. It's also about geometry. A massive eruption pointed away from Earth may have little effect on us. A smaller one aimed directly toward Earth can have a much greater impact. That is why scientists never judge danger by flare size alone. Every event must be analyzed individually. No guessing, just the facts. What would a superflare actually do to Earth? Forget Hollywood for a moment. A superflare would not ignite Earth's atmosphere. It would not boil the oceans. It would not instantly wipe out humanity. Those scenarios belong in fiction. The real concern is far more complicated and, in many ways, more unsettling. Modern civilization depends on something you almost never think about: electricity. Every second, millions of computers exchange information through fiber optic cables, data centers, satellites, and wireless networks. Banks synchronize transactions using signals from navigation satellites. Power stations constantly balance electricity across thousands of kilometers. Air traffic controllers monitor aircraft moving at nearly the speed of sound. Emergency services rely on communications that operate every minute of every day. Most of these systems work so reliably that they become invisible, until they don't. When a major geomagnetic storm reaches Earth, it pushes against our planet's magnetic field. That motion generates electric currents, not inside the sun, inside Earth itself. These are called geomagnetically induced currents. Long metal conductors become pathways for those currents. High-voltage transmission lines, oil and gas pipelines, railway signaling systems, undersea communication cables. The longer the conductor, the greater the potential for induced electrical currents. Large transformers are among the most vulnerable components. These transformers are enormous. Many weigh hundreds of tons. They cannot simply be replaced overnight. Some require months, or even longer, to manufacture, transport, and install. If enough of them failed simultaneously, restoring portions of the electrical grid could become a prolonged challenge. That is one reason power companies now work closely with space weather agencies. Preparation matters. Satellites face different risks. Outside Earth's atmosphere, spacecraft receive little natural protection from energetic particles. Radiation can damage electronics, corrupt memory systems, disrupt onboard computers, interfere with sensors. In severe cases, permanently disable satellites. Astronauts face additional concerns. Earth's magnetic field normally shields people on the surface from most solar radiation. Astronauts living aboard the International Space Station remain partially protected because they orbit within much of that magnetic shield. Future crews traveling to the Moon, or eventually Mars, would have far less protection. For them, an extreme solar event could become a serious radiation emergency. Communication networks could also be affected. High-frequency radio signals reflect from Earth's ionosphere. Solar storms disturb that layer. Military operators, emergency responders, commercial aviation, maritime shipping, all depend on reliable radio communication under certain conditions. Disruptions may last minutes, sometimes hours, occasionally longer. Again, much depends on the characteristics of the storm itself. And yet, despite all these risks, Earth has one enormous advantage. Our planet possesses a powerful magnetic field. It acts like a giant shield, extending tens of thousands of kilometers into space. Without it, life on Earth's surface would face far greater exposure to charged particles from the sun. That invisible shield absorbs much of the impact before it ever reaches us. It's one of the reasons Earth has remained habitable for billions of years. The sun provides the energy that makes life possible, and Earth's magnetic field helps protect that life from the sun's most violent moods. No guessing, just the facts. Have superflares happened before? If the sun can produce a superflare, has it already happened? The honest answer is, scientists aren't sure. Human civilization has only observed the sun with modern instruments for a tiny fraction of its lifetime. The telescope has existed for just over 400 years. Satellites have monitored the sun for only a few decades. Compared to the sun's age of approximately 4.6 billion years, that's almost nothing. So researchers search for evidence elsewhere. One place they look is in ancient trees. Every year, trees form a new growth ring. Those rings preserve tiny amounts of radioactive carbon, known as carbon-14. Normally, carbon-14 forms when high-energy cosmic particles strike Earth's atmosphere. Occasionally, however, scientists discover sudden spikes. One of the most famous occurred around the year 774 to 775 CE. Tree rings, from multiple continents, recorded an unexpected increase in carbon-14. Another event appears around 993 to 994 CE. Something dramatically increased the amount of energetic particles reaching Earth. But what? Some researchers suggest unusually powerful solar activity. Others argue the source could have been a different cosmic event. The exact cause remains under investigation. No scientific consensus has identified these events as confirmed solar superflares. They remain intriguing clues, not proof. Ice cores collected from Greenland and Antarctica provide another record. Layers of ancient ice-trap chemicals produced during periods of intense solar activity. Combined with tree ring evidence, they allow scientists to reconstruct parts of the Sun's history, extending back thousands of years. These natural archives suggest the Sun has experienced periods of activity stronger than anything recorded during the space age. How much stronger? That's still uncertain. And uncertainty matters. Science advances by testing evidence, not by filling gaps with dramatic stories. That is why researchers continue comparing ancient geological records with observations of sun-like stars. Each new discovery adds another piece to the puzzle, slowly, carefully, without assumptions. Because understanding the Sun isn't just about satisfying curiosity, it's about understanding the only star humanity will ever depend on. No guessing, just the facts. How scientists are preparing for the next extreme solar storm. If there's one lesson from every major solar event in history, it's this: preparation matters more than prediction. Scientists cannot stop the Sun. They cannot prevent a solar flare, but they can learn to understand it. Across the world, an international network of observatories watches the Sun every hour of every day. NASA's Solar Dynamics Observatory photographs the solar surface in multiple wavelengths every few seconds. The ESA NASA Solar Orbiter studies regions of the Sun that have never been viewed in such detail before, including higher solar latitudes. The SOHO spacecraft, launched in 1995, continues monitoring the solar corona and tracking coronal mass ejections as they leave the Sun. On Earth, the NOAA Space Weather Prediction Center analyzes incoming observations around the clock. When a significant solar event occurs, alerts are sent to governments, satellite operators, electric utilities, airlines, and other industries that could be affected. Power companies have developed procedures to temporarily reduce stress on critical transformers. Satellite operators can place spacecraft into protective configurations. Airlines can reroute flights away from polar regions when radio blackouts become more likely. Astronauts aboard the International Space Station can take shelter in areas with greater shielding during periods of increased radiation. These aren't hypothetical plans. Many are already part of routine space weather operations. Governments also conduct exercises based on severe solar storm scenarios. Emergency agencies test how communication systems, transportation networks, and electrical infrastructure would respond if a major geomagnetic storm struck today. The goal isn't to eliminate risk. That's impossible. The goal is resilience. Every improvement in forecasting gives operators more time. An extra hour can protect a satellite. Several hours can allow utilities to prepare the electrical grid. A full day can dramatically reduce potential disruption. This is why space weather has become an increasingly important field of scientific research. Not because catastrophe is certain, but because modern civilization has become deeply connected to technologies that depend on conditions in space. The better we understand the Sun, the better we can protect ourselves from it. No guessing, just the facts. For thousands of years, humanity worshipped the Sun. Farmers depended on it. Sailors navigated by it. Entire civilizations built calendars around it. Today, we understand it far better than our ancestors ever could. We know its age, its temperature, its magnetic cycles, its nuclear engine. We watch it continuously, with spacecraft orbiting millions of kilometers from Earth. And yet, the Sun still surprises us. The discovery of superflares on Sun-like stars reminds scientists that our nearest star may still hold unanswered questions. Can the modern Sun produce a true superflare? Some evidence suggests it might be possible. Other researchers argue the probability is extremely low, or that today's Sun may lack the magnetic conditions required. The debate continues. That uncertainty is not a weakness. It's how science works. Researchers collect evidence. They challenge their own conclusions. They improve models. They revise ideas when new observations appear. The important fact is this: the Sun is neither perfectly predictable nor completely mysterious. It is an active star governed by the laws of physics. Most of the time, those laws produce the sunlight that warms our planet and makes life possible. Occasionally, they produce solar storms powerful enough to remind us that Earth exists inside the atmosphere of a star. And somewhere among billions of sun-like stars across the Milky Way, Astronomers continue watching. Every observation brings another clue. Every mission answers one question and raises another. Because the biggest mystery isn't whether the universe is dangerous. It's how much we still have left to learn about the one star we thought we knew best. No guessing, just the facts. End of script.